Hello. We have a problem here that describes a capacitor situation. Um, and essentially it says we have two uncharged parallel plates. One's going to be this top one. I'll just go ahead and call this T for top. And one's this bottom one, the same plate. And then we ground those things. And then we take a positively charged plate and we slide it in the middle there. It's a thin plate here. And it has a positive charge on it, and it's a distance d from the top and a distance 2d from the bottom. So that's like the position between these two plates we put it. And we're asked, what's the voltage on these plates? And then we're asked about what's the charge. So voltage top and delta voltage of the bottom. And then we're asked about the charge of the top and the charge of the bottom. Okay, so we'll jump here and try this out. I'm actually going to go for this one first. We'll go for this one. So well, let's talk about fundamental ideas here. When we hook this up and put it in there, there's going to be some current that flows around a little bit here, but eventually it's going to reach steady state. And when I hook something up to ground readily volunteers to let electrons go and try to ground stuff out. So when I put this positive charge next to this neutral plate that's connected to ground, the ground's going to sense this is next to something very positive, and electrons are going to want to rush in and try to neutralize things. And so that's going to stack electrons on here. Maybe like that. Like, man, it's pretty close to this positive thing. Probably a lot of them will go over there. And we're going to have an electric field between these because of that. And if I put a positive thing in the middle of this positive plate and this guy, it would be pushed this way. And I'll just draw it like this. It's going to have maybe a pretty good field. Okay, that's my E field. Okay, but the same thing is going to be noticed over here. This plate is also connected to ground, and it's like, oh man, there's a positive thing over here, and electrons are going to rush onto here too. Electrons are going to be like, ooh, that's very interesting that we have a positive thing over here. I would like to be next to that. But it's a little bit further away, so they're not quite as excited. It's not quite as close and exciting there. So we're going to have something like this, and that E field's going to be not as strong. So I'm going to make it a little bit thinner. The density is not quite as much. Okay, so I don't know. We'll call this the top, and we'll call this the bottom electric field. Okay, so we're looking good here. All right. So charge is going to flow onto here until it reaches an equilibrium position where the voltage is equal everywhere that there's a conductor. So this top plate is connected by a wire to ground and also to this bottom plate. So this is all one big conductor. Maybe do I have a highlighter up in here? Let's see if I can do some. No, freehand. Yes, freehand highlighter. Okay, let's do this. So this is going to be all one piece of metal, and charge is going to flow until the voltage is the same everywhere on here. Because charge likes to flow spontaneously to lower voltage levels. Well, it's going to distribute until it reaches the same voltage across all this stuff, and that's going to be equilibrium, steady state. So in other words, what I'm trying to say here is that the change in voltage here has got to be equal to change in voltage here. Now I'm missing one spot. The voltage difference includes this little plate here. So I got to talk about that too. So let's talk about that. Let's see here. Okay, so the positive charge here is also going to distribute to accommodate this situation also. So this is a metal conductor. Charge can flow freely across it. And charge is going to distribute in such a way that, ooh, man, I got a lot more negative on this side, and not as much negative over here. So it's going to distribute until it reaches equilibrium also. And so we're going to, more of the charge is going to be stacked on this side. And this takes forever. I'm so sorry. So sorry. Should have had a picture already done for this. I apologize. Okay, and then some of the charges can be like, hey, there's some negative over here, so we're going to hang out over here too. Not as much. Not as much. Because there's not as much exciting negative stuff over here. So we're going to have a different amount of charge on the top plate and a different amount of charge on the bottom plate. Okay, and we can call this, ooh, maybe what color we're going to do. We're going to call this Q top. And we're going to call this Q, oh, come on. My mouse is misbehaving. Q bottom, right? It's going to have two different amounts of charge on top and bottom. Okay? And that's what we would like to solve for right here. So let's go ahead and start writing down some fundamental ideas about some physics. So the total charge is plus Q, right? So we're going to do charge conservation here. Well, a bunch of it goes to the top, and some of it goes to the bottom. Okay, and charge is going to distribute on here until it reaches equilibrium in this middle piece. And so the voltage is going to be the same everywhere on here. So the voltage on the top is going to be equal to the voltage on the bottom. So the difference from this side to this side is going to be the same as the voltage difference from here to here, because the voltage right here is the same as the voltage right here, and the voltage right here is the same as the voltage right here, because everything's in equilibrium. Okay, that's why we have the same voltage difference from this to this and from this to this. So I'm going to go ahead and say, because of equilibrium, oh man, I should just type instead of hand draw on this, equilibrium or steady state for our charges. Oh, man. We can go and say, well, delta V, the top, is equal to delta V of the bottom, which is, we're just going to call it all delta V, if that's okay with you, since they're the same. All right. Okay, the next thing, let's talk about capacitance. Capacitance of the tippity top. So there's a capacitance between these parallel plates right here. Okay, so the charge of the top compared to the voltage difference across there, just delta V. Okay, that's what a capacitor does. It stores charge for a certain amount of voltage. Okay, and I'm going to come over here. Man, I wonder if I should organize this better. Okay, we're good. Okay, I'm going to do the same thing for the bottom. Capacitor of the bottom is going to be the charge of the bottom compared to the voltage difference. Okay, that's fine. I'm going to take this little idea here. I'm going to put it in this color. Hey, what's the capacitor do? How do you build a capacitor? We have this equation for how you build a capacitor. You have the constant. You got your how big the capacitor's area is, one of those plates, and we got the separation distance, D. Let's keep that in mind right here. I'm going to kind of use that next. All right, so let's go ahead and put it in. Instead of this capacitance at the top, we're going to put in all the stuff about the top. It has a separation distance, D, and all these areas are the same. So I'm going to go ahead and say, Ayo. A, and the top one is just a separation distance D, and we got Q top, oh, come on, top, and we got delta of V. Okay, and so that's like this guy. All right, and this guy, we're gonna go ahead and do the same thing, kind of thing. EO, A, but this one is 2D part. Okay, and we got Q of the bottom, and we got delta V. Okay. So how about we solve this for delta V, and then we can plug it on in over here. So delta V is equal to QB. And what we bring this over to the other side, we're going to have 2D. Yeah. That. Okay. I'm going to go ahead and put this stuff in right here. Ding. Over there. All right, let's do it. Okay, so we still have the left-hand side. Man, my mouse writing is a little bit sloppy. Sorry. Q top. But for this bottom bit, we're going to put in this stuff. So we got Q bottom. We've got 2D. We've got, it flips it on top here, EOA. Now I can go ahead and get rid of a bunch of stuff. Hey, that's on this side. That's on the other side too. We got a D. Okay, cool. And we can get to a final statement. Basically, I'm going to take these two things, put it on the left-hand side, and I'm going to say Q tippity top is equal to 2 Q bottom. Yes! I love it! We knew this would happen! Look, the top is closer. It's going to allow electrons to get closer to this really attractive positive charge. It's going to stack more over here. This side is not going to have quite as many. Look at that. All right, cool. So now what do we do? Well, we want to solve for actually how much this is. We got what proportion this is, and you can probably do it in your head from now if you want, but I'm just going to go ahead and spell it all the way out. Okay? So what can we say? We can say there's a total charge Q that they told us. I don't know, some number. Instead of top, though, we can say 2Q bottom. Twice as much, right? Plus Q bottom. How many Q bottoms do we have here? We have Q is equal to 3 Q bottoms. Well, so what? That means Q bottom is equal to a third of the total charge. So what does that mean for Q top? Q top must be equal to 2/3 of the total charge to make this work out. There's our charges. Yeah. Okay, so how about this voltage? What is this voltage difference of this capacitor and this capacitor? Well, they should be the same. And basically, we can just take either one of these answers and plug it back into either this capacitor equation or this capacitor equation. We can solve for it. Now, I neglected to mention, they told us the plates' areas were A for all of them, and they were the same. So that's a known value. So we can come over here and we can say, well, which one do we want to do? I don't know. Let's do the top, I guess. All right, we can say, hey, let's check this out real quick. So we can say EOA over D is equal to Q top. But what's Q top? Q top was 2/3 Q. 2/3 of the total charge Q compared to delta V. And from there we can get V on top here. So we're going to go ahead and say delta V is equal to 2QD over What are we going to have down here? We're going to have a 3, and we're going to have a EO A. And there we go. There's that little guy. And that should be the same for both of those. So we could have plugged it in over here and got the same result. So anyways, that's how we solve a problem like this. So just to recap, we had 2 uncharged plates. We hooked it up to a ground. We slid a positive charge in here, and that's going to draw electrons from ground towards this positive plate that we slid in there. Since it's close to the top one, boy, those electrons are going to be able to stack a little bit more on this top plate. And since it's further away, they're going to come over here a little bit less. But we're still going to have distribution. Okay, that's also going to inspire this middle plate to have more of its positive charge be left up on top, and some of its positive charge go on the bottom. So basically more electrons are going to go away from this top side and be more on this bottom side is really what's happening. Okay, so anyways, and they're going to move around until this whole surface gets to the same voltage, and there's no advantage to fall to a lower energy level. And the same thing is going to go on here. This is going to redistribute its charge until it all reaches the same voltage and there's no spontaneous movement of charge. So that we have the voltage drop across these 2 different capacitors are the same. And that's a foundation for our thinking. Okay, and then we can employ what it means to be a capacitor. I store charge for a certain amount of voltage for both the top and bottom. We employ how you build a capacitor. So we plug that into the left side of both these equations. And we're able to substitute these together to get a ratio of the charges, plug that into a conservation of charge kind of setup here, okay? And we can solve for how much is on each plate. After that, we just cycle it back into one of these capacitor equations and we can get the voltage. All right, so super important to understand what steady state is. It's when charge stops moving around, charge stops moving around when voltages are all the same. All right, I hope that's helpful. Have a good day.